Morning students. So in this video we can discuss a roadmap type question. Question is in the board. Starting from methane. First chlorination, capital A, treating with metallic sodium ether, product B, then chlorination C, alcoholic AOH D, bromination then E, then again alcoholic AOH F, passed through an iron tube, hot iron tube G, nitration reaction H, reduction using single HCl I, diazotization J, the solution on warming K, finally K1 treating with the chloroform and alkali L. So what is L in this roadmap type of question? Starting from methane. Okay, we can start that roadmap type of question. So starting from methane, CH4 plus chlorine, a photochemical reaction by free radical mechanism, that is a substitution reaction, minus HCl and CH3Cl, capital A, that is capital A. Methyl chloride or chloromethane, methyl chloride or chloromethane, that is capital A. That methyl chloride alkyl halide when treating with a metallic sodium in dry ether medium, dry ether, alkyl halide and metallic sodium in dry ether medium, reaction is Woods reaction, alkyl halide 2 molecules, metallic sodium Na, solvent dry ether minus 2 NaX and RR is alkane, reaction is Woods reaction. So A to B is Woods reaction, Woods reaction, A to B is Woods reaction. That is methyl chloride 2 molecules, metallic sodium 2 atom, dry ether. So minus 2 NaCl, minus 2 NaCl and alkane RR CH3 ethane. So B is ethane. This is a B is ethane. So methane to ethane, methane to ethane. Then B is ethane, CH3 single bond to CH3. Again chlorination, photochemical reaction with the free radical mechanism, chlorine in presence of light, H and Cl minus HCl and CH3 CH2Cl, that is C, ethyl chloride or chloroethane, ethyl chloride, ethyl chloride, and we reach up to C, that is C is ethyl chloride. Then C to D reagent alcoholic potassium hydroxide, alcoholic caustic potash. So C is chloroethane or ethyl chloride, ethyl chloride, CH3 CH2Cl plus KOH, not aqueous, alcoholic KOH, alkyl halide and alcoholic KOH reaction, dehydrohalogenation or beta elimination reaction. So this is alpha carbon, halogen linked to this carbon, and this carbon is called alpha and this carbon atom is called beta carbon. From alpha carbon, halogen is removed, chlorine combines with K and KCl is removed. From this alpha carbon, chlorine atom is removed. From beta carbon, one H atom is removed as water, combines with OH, H2O. So from alpha carbon, chlorine is removed, beta carbon, H is removed, and the single bond becomes a double, and the product is CH2 double bond CH2, ethylene or ethene, that is capital D, ethylene or ethene, ethene. So from alpha carbon, halogen is removed, From beta carbon, hydrogen atom is removed. Totally HCl is removed. Hydrogen halide is removed. Removal of hydrogen halide, dehydrohalogenation reaction. Since H atom is removed from beta carbon, this reaction is also called beta elimination reaction, and the product is an alkene. Alpha carbon halogen, beta carbon H, and this single bond becomes a double, a compound becomes unsaturated. So after elimination reaction, saturated compound becomes unsaturated, and ethene is capital D. Dehydrohalogenation or beta elimination. So then D to E. So ethene, that is a capital D. On treating with the bromine, electrophilic addition reaction, electrophilic addition. One bromine atom here, another bromine atom here, double bond becomes single. So after addition reaction, unsaturated becomes saturated. After elimination, saturated becomes unsaturated, and after addition reaction, unsaturated compound becomes saturated. That is CH2Br, single bond CH2Br, and this is capital E, D to E. So this is ethylene and this is bromine, ethylene bromide, ethylene bromide, ethylene bromide, IUPAC, 1,2-dibromoethane, 1,2-dibromoethane. That is a dihalide. That is a vicinal dihalide. Halogen atoms are present in the adjacent carbon atom. That is why that is a vicinal dihalide, 1,2-dibromoethane, and that is capital E. Capital E into capital F. Reagent alcoholic avoid. Reaction is dehydrohalogenation or beta elimination like this step, C to D. Then E to F. E to F. E is ethylene bromide. E. So CH2Br, single bond CH2Br, and the reagent is alcoholic AOH. So this is a dihalide. This is a dihalide. So beta elimination reaction takes place in two steps. So we can say this is alpha carbon first and this is beta carbon. From alpha carbon bromine and beta carbon H, totally HBr minus HBr, dehydrohalogenation. Br as KBr, H as water. So simply we can write like this: alcoholic AOH is the reagent, then elimination reaction or dehydrohalogenation reaction from alpha carbon halogen, beta carbon H, totally HBr. The saturated compound becomes unsaturated, and the first intermediate is CHBr double bond CH2. This is a halide, that is again alcoholic AOH. So elimination reaction in two steps because this is a dihalide. Then this is the alpha carbon, hydrogen linked to this carbon, and this is beta carbon. From this alpha carbon bromine is removed, and from this beta carbon H is removed, totally HBr, and this unsaturated compound becomes more unsaturated and a double bond becomes a triple, that is the product is acetylene or ethyne. Ethyne or acetylene is produced. So E to F. So this is E to F. This is F acetylene. F is acetylene. Okay. Then F to G. That is this acetylene gas is passed through a red hot iron tube. Polymerization reaction takes place, that is trimerization. So F is acetylene, CH triple bond CH or C2H2, that is F. So C2H2, that is F acetylene. When passed over a red hot iron tube, trimerization takes place, polymerization, and benzene is obtained. Aromatic hydrocarbon benzene is obtained. So methane into benzene. So aromatic hydrocarbon benzene is produced. Benzene, methane into benzene, that is G. Trimerization. So G is benzene. Okay. And then G to H reaction, nitration reaction. Reagent is nitric acid and sulfuric acid. Reaction is electrophilic substitution reaction. So this is benzene. This H is exposed and nitric acid HNO3, that is OHNO2, HNO3 and catalyst sulfuric acid. Electrophilic substitution reaction, SC. So H and OH minus H2O and nitrobenzene is the product, nitrobenzene. So nitrobenzene. So H is nitrobenzene, G is benzene, G to H, nitration reaction. Benzene on nitration, nitrobenzene. Reaction, electrophilic substitution reaction. So H is nitrobenzene. So H to I, nitrobenzene on reduction, NO2 on reduction, nitrobenzene on reduction using zinc and HCl. Zinc and HCl is the reducing agent. So 6H or 3H2 from zinc and HCl, zinc, chloride and H atom. So 6H. 2 oxygen atom is removed as water, so minus 2H2O. H2O, H2O, remaining 2H, that is NH2. So nitrobenzene is changed into aniline. Aniline. When NO2 is reduced, it is changed into NH2. Oxygen atom, 2 oxygen atoms are removed as water and 2 H atoms are connected there and thereby aniline is produced. Aniline. So aniline is I. So H to I conversion. Aniline. So methane to aniline. Then I to J. I to J. I is aniline. NH2, aniline. When treating with sodium nitrite and HCl at 0 to 5 degrees Celsius. 0 to 5 degrees Celsius. This reaction is called diazotization. Diazotization. After diazotization, NH2 is converted into N2Cl. NH2 is converted into N2Cl overall. So this is the product. N2Cl, NH2 is changed into N2Cl. Benzene diazonium chloride. Benzene diazonium chloride. Benzene diazonium chloride. Onium chloride. Benzene diazonium chloride. This is J. So I into J. J is benzene diazonium chloride and this process is called diazotization. Reagent sodium nitrite and HCl. NH2 is aromatic amino compound. NH2 is converted into N2Cl. That is benzene diazonium chloride and that process is called diazotization. Then J to K. J to K. J is benzene diazonium chloride. Benzene diazonium chloride. Solution on warming H2O. Solution on warming. N2 removed as N2 gas. Cl removed as HCl. And OH will connect there and phenol is obtained. Phenol. Phenol is obtained. So K is phenol. J to K. So methane to phenol. Phenol is obtained. Then K to L. Final step K to L. That's an important name reaction. K to L. That is phenol. Phenol. When treating with chloroform and alkali. CHCl3. Chloroform and alkali gives Cl. That is the final step. Phenol, chloroform and alkali. So phenol, when treating with the chloroform and alkali NaOH. Phenol. In presence of alkali, phenol is changed into sodium phenoxide. H and OH water, sodium will connect here. And phenol is ortho-para-directing. So OH group is having plus R effect or plus M effect. OH group is an activating group. It is an ortho-para-directing group. So the incoming electrophile will attack at ortho or para position. This position is ortho and this position is para. So the incoming electrophile will substitute either in this ortho position or para position. So we can take the ortho isomer. So H is here, H and Cl minus HCl. So the first product, OH first converted into ONA because the reaction is carried out in presence of an alkali. H and OH water, OH becomes ONA, and the second step H and Cl, HCl, and here CHCl2 in the ortho position. In the same way, reaction takes place in the para position also because OH group is ortho para directing, or it is an activating group, or this group is with a plus resonance effect or plus mesomeric effect. So this is the first intermediate. Alkali change OH into ONA, and this chloroform attack at the electrophile attack at ortho position, and the intermediate product is H is removed as HCl, and then CHCl2 will connect there classically, and again NaOH. Two chlorine atoms are replaced by means of this powerful nucleophile OH minus, 2 NaOH minus 2 NaCl. Cl removed, 2 OH will connect there, 2 OH will connect there, ONA and CHOH OH. This is a highly unstable compound. Carbon is unable to accommodate two bulky OH group, so water is removed and this part becomes CHO, aldehyde group. So this is ONA and this is CHO. And further acidification, HCl, NaCl, and this is the final answer. ONA becomes OH, we retain the OH, and it is CHO. So K is phenol. K is phenol. After adding chloroform and alkali, phenol K, after adding chloroform and alkali, and a CHO group is introduced in the ortho position. An aldehyde group is introduced in the ortho position. In the same way, CHO group can be introduced in the para position also. And this compound is this is benzaldehyde, and this compound is ortho-hydroxy benzaldehyde. Ortho-hydroxy, and this product is ortho-hydroxy benzaldehyde. Benzaldehyde, also known as salicyl aldehyde. Salicyl aldehyde. So answer L is salicyl aldehyde. Ortho-hydroxy benzaldehyde. Para-hydroxy benzaldehyde is also produced. In the same way, K is phenol. After adding CHCl3 and NaOH, CHO group is introduced into para position also. So this is benzaldehyde and this is para-hydroxy benzaldehyde. But this product is a minor product and this is the major one. This is the major one and this is the minor product. So we considering only the major product, ortho-hydroxy benzaldehyde known as salicyl aldehyde, and the conversion K to L is called a Reimer-Tiemann reaction. A Reimer-Tiemann reaction, K to L. Conversion of phenol into K is phenol into salicyl aldehyde using chloroform and alkali, and this reaction is called a Reimer-Tiemann reaction. So we can check the mechanism of this reaction. This is a Reimer-Tiemann reaction, and L is the major product. We are considering only the major product, and K is phenol. K is phenol and L is salicyl aldehyde, and OH here it is CHO, and the minor product is this one. This is phenol. In the same way, CHO can introduce into para position also because phenol is OP directing, and this ortho isomer is the major product and this is the minor product. This reaction is called Reimer-Tiemann reaction. Why this becomes the major product? A reason, intramolecular hydrogen bonding or chelation. This is phenol and this is CHO, aldehyde group. They are in the Nearest position, carbon number 1, carbon number 2. So H carries delta plus, O carries delta minus polarity. O carries delta minus, C carries delta plus. Oxygen is more electronegative, carry delta minus. And H carry delta plus. Attractive force between this positive pole and the negative pole, and this bond is called, this attractive force is called the hydrogen bond, and it is an intramolecular hydrogen bonding that makes this compound highly stable. That is why salicylaldehyde becomes the major product. That hydrogen bonding is not operating in this molecule because they are at a 1,4 position, but here it is at a 2,1,2 position. OH and CHO. Here hydrogen bonding is not operating. Which hydrogen bonding? Intramolecular. That is why salicylaldehyde becomes the major and this becomes the minor, and the reaction is called Reimer-Tiemann reaction. So we are considering L as the major one, that is salicylaldehyde is the final answer. So by this roadmap question we convert methane into salicylaldehyde, orthohydroxy benzaldehyde. So we can discuss the mechanism of this Reimer-Tiemann reaction. So this is Reimer-Tiemann. Phenol, chloroform and alkali. Ortho CHO group will introduced mainly at ortho position due to this generation. This is a Reimer-Tiemann reaction. This is salicylaldehyde, benzaldehyde, orthohydroxy benzaldehyde. We can discuss the mechanism of this reaction, Reimer-Tiemann reaction. This is an SC reaction. Reimer-Tiemann reaction is an electrophilic substitution reaction. So phenol, chloroform, alkali followed by acidification. Chloroform, alkali followed by acidification. Orthohydroxy benzaldehyde. So orthohydroxy benzaldehyde, salicylaldehyde, salicylaldehyde. This reaction is a Reimer-Tiemann mechanism. So phenol first changed into phenol in presence of alkali, NaOH. OH changed into ONA, a strong electrolyte. H and OH water, salt and water, sodium phenoxide. The sodium salt is a strong electrolyte. Acid and base salt, sodium phenoxide, a strong electrolyte. So step 1. The sodium phenoxide ionizes into sodium phenoxide. One way is because this is a strong electrolyte. Phenoxide anion, O minus and Na plus, and phenoxide anion. This is the substrate. Phenoxide anion. This phenoxide anion, like phenol, it is also ortho-para-dialectic. So this is a phenol. So phenol first converted into phenoxide anion. Then this is an electrophilic substitution reaction. The second step is, this is step 1. Step 2, generation of the electrophile. Electrophile will produce by the reaction between chloroform and alkali. So in the first step we produce, in the step 1, we produce the phenoxide anion. Phenoxide anion, okay? Second step. So phenoxide anion is there in the first step. Step 2, generation of the electrophile. Step 2. So reaction between chloroform and alkali, CHCl3 and NaOH. The reaction is an alpha elimination reaction. So far we discussed the beta elimination. Alpha elimination means two groups are removed from same carbon. Beta elimination means the groups are removed from adjacent carbon, alpha, beta. So here only one carbon atom in chloroform. Two groups will remove from that carbon atom, and thereby an intermediate is produced. An electrophile will produce. An electron deficient species will produce. So chloroform. So NaOH ionizes into Na plus and OH minus base, chloroform CHCl3 chloroform. It undergo alpha elimination in presence of this base. So OH minus will abstract this H as H plus without taking the bond pair. This is a pair of electron and H atom removed without taking this bond pair. So from carbon atom, one of the atoms, that is H atom, removed without taking its bond pair as H plus. So minus H2O, and the resulting is CCl3, and this carbon gain an extra electron from this H atom, electron of carbon, electron of H atom, extra one electron. Carbon outermost shell 4 electron, now 5. 1, 2, 3, 4, 5. So it carry a minus charge. And anion is produced. So from chloroform, H is removed. Again from this intermediate, one chlorine atom is removed as a chloride ion Cl minus. It is removed by taking the bond pair. Second atom, first H atom is removed without taking the bond pair. In the second time, one of the chlorine atoms removed by taking its bond pair, that is, it is removed as a Cl minus by taking this electron also. A minus Cl minus, that is Na plus minus NaCl, Na plus and Cl minus. So two atoms removed from this carbon. One is H as H plus and another chlorine as a chloride ion. And when two atoms removed from the same carbon, elimination reaction is called alpha elimination reaction, and the resulting product is an important product, a carbon with a 2 chlorine atom and with a pair of electrons. No charge. When H plus removed, it occur a negative charge. In the second case, Cl is removed as a Cl minus. So net result that carbon becomes a neutral. So this is the electrophile. This electron loving, because it has a deficiency of a pair of electrons, like a carbocation. Outermost shell of carbon, bond pair, unshaded pair, total 3 pairs. Pair, total 6 electrons. Unstable. It has a deficiency of a pair of electrons to become octet. 2, 4, 6. So this is a neutral electrophile. So in Reimer-Tiemann reaction, the electrophile is a neutral electrophile, dichlorocarbene, a neutral electrophile. This will attack the phenoxide anion in the ortho or para position. The ortho isomer is the predominant product, that is why we will attack this dichlorocarbene at the ortho position of phenoxide anion. In the first step, we produce the phenoxide anion, and in the second step, the electrophile. The reaction is electrophilic substitution. All aromatic compounds undergo electrophilic substitution reaction because all aromatic compounds containing delocalized pi electrons. They are electron rich. This is electron deficient. So this is electron deficient carbon intermediate carbene will attack at which position? Ortho position, because that anion is which directing? Ortho para directing. Phenol is OP directing. Phenoxide anion is also OP directing. So dichlorocarbene, neutral electrophile. So finally, the attack between this phenoxide anion and dichlorocarbene leads to the formation of which product? Salicylaldehyde. Okay. So phenoxide anion and dichlorocarbene. Yes, electrophilic substitution. So this is phenoxide anion, 3 pi bond, O minus, electron deficient intermediate dichlorocarbene with a pair, deficiency of a pair of electron. So electromeric shifting like this, first shifting, number 1, number 2. And H is already present here at the ortho position, and H is present at the ortho position, and this is the first migration and this is the second one. And the resulting is the dichlorocarbon attack at ortho position, ortho carbon. So carbon-carbon bond is produced, and these are the steps. This H is already there, and CCl2, a pair is there. Now this carbon get an extra electron, one electron, thereby it acquire a negative charge from this pi bond. It acquire an extra electron, a new bond is formed, then it acquire a minus charge, double bond here, double bond here, double bond O. This bond becomes double. In the next step, this pair inside, step 1, step 2. This bond becomes double. O carries the minus charge, H removed as H plus, and that H plus will connect to this negatively charged carbon. So the intermediate is, the changes are like this. This bond becomes double, this bond becomes double, this bond becomes double, this bond becomes single, O becomes a minus, and Na plus will connect there, O Na and C there, H plus will connect in this minus charge, CH and Cl2. This is about a Reimer-Tiemann reaction. Further step, you know the further step. Again NaOH. 2 chlorine atoms are replaced by 2 OH group. So minus 2 NaCl, and finally the product is so ONA and CH, OH, OH, and steric factors. Carbon is unable to accommodate 2 OH group, dehydration, minus H2O. So the answer is ONA and CHO. On acidification, final step, HCl minus NaCl and orthohydroxybenzaldehyde known as salicylaldehyde is obtained, and this is the mechanism of Reimer-Tiemann reaction. Okay, thank you.